Anthony also is not coming, but thank to them and to the two who are here anyway. When I was given the instructions, when I was asked to give a plenary or keynote, Anthony said to me, can you do some applications, some industrial application in your talk? And of course, I mean, yesterday, I thought, well, probably I should put from fundamentals to applications just to make sure that I do my homework. But I was also a little bit scared because after listening to Rodney yesterday morning, I'm like, oh my God, I mean, it's like I don't have so much mathematics in my talk. So I hope that it's going to be okay for the audience here. Another thing was that I didn't realize when I said yes that I had to speak for an hour. So now I can speak a lot actually. I can keep speaking. However, you know, I also would like that people do not start to sleep and also that people find some interest in this. So let's see how it goes, and I will look around, and if people are sleeping, I just go faster and then try to do in less time. So first of all, these are most of the contributors to this talk, and the majority of the work is actually not really my work because it's my PhD students and my postdocs and my colleagues that have contributed a lot to this, and one of my colleagues just sitting over there, Ali, yesterday gave a nice talk about ribocharging. So let's see what comes. Now, the other thing, see, I've done my homework. Yesterday, I also was reading a little bit about the introduction to this, and clearly there was the 21st century energy mix. So when I'm speaking about applications, I'm trying really to see if I can relate what I'm doing to the 21st century energy mix. And I thought that this diagram here, this graph, is very interesting because actually you can see that biomass is not something completely new. Actually, we were using a lot of biomass, burning wood. And then, of course, I mean, it went down as the coal and the oil started to, the oil especially started to take off. But I think the more interesting, it's really the projection will say that we have to have a mix. And the important point is that if you look at how we use biomass, coal, oil, and gas, and so on, there is always some particle technology, some granular flow, some fluidization, something there which is going to be used. So I think that we are in a very good position really to make an input in this. And if nothing else, just to understand better some of these operations and how they can affect what we are actually doing. Now, this is the big vision, and this is the work that I'm working on at the moment, starting the end of 2016 for 5 years. And the other thing which was also very nice to see on the booklet yesterday was this micro, meso, and macro, because I think that that is exactly what I'm trying to do. I'm trying to do some mainly modeling at the multi-scale side of all the story. But of course, I mean, you realize that sometimes you have to do also some experiments, and I will try to present to you some experimental work which we have started very recently actually, so I have just some preliminary results about that. This is the vision of my work, like I said, and this is also something else which I would like to point out. What we wanted to do and what my proposal was about, this is actually money which comes from the Research Council in the UK. I was trying to develop an user-inspired theory. And that's why I think that the application is very relevant in this situation. Now, for the ones of you who live in the UK, you know this is a buzzword. If we use user-inspired theory, this is much more likely that we are going to get funded. But nevertheless, we have to deliver.
Wouldn't it be just professor-inspired?
So anyway, we have to deliver, and I think that it's actually, we have to work towards impact, and therefore I think that's okay. Now, this is, like I said, it's a personal fellowship which aims just at looking at the micro the macro and the meso, of course, because we realized very soon that if we don't understand the meso scale, we are not able to do the work at the macro. Now, and this is what I listed like the deliverables, and really this is where I'm working at the moment, constitutive models and reliable measurements. And of course, I mean, there is the idea of also improve some CFD codes that we are using, and the translation, which is industry. But, and also, I always forget to say something about that, but I think that, I don't want to preach here, but I think that it's sometimes, and I'm speaking more for my country, well, I have two countries really, but one of my two countries where really we don't do enough to train the next generation. And I think that it's also extremely important that we don't teach always the same identical stuff. I mean, most of my students don't know what is meso, and I think that we have to start to tell them that, you know, there is something in between that we need to understand. Now, going back to the particle interactions, and that is what I'm going to concentrate mainly today. In fact, I mean, I said I'm going to speak about wet particles. We are here. We have the rapid flow regime, and I think that we have used and misused and overused the kinetic theory for this kind of flow. We have the slow friction regime, and we know that, again, we have been mainly modeling it through the Coulomb frictional law. However, there are so many situations where the intermediate regime developed, where you have coexistence of frictional and collisional stresses. And therefore, that is where I really would like to understand better what's going on. Honestly, I have to declare my ignorance. I don't know what really physically, what is actually happening there. I really would like to understand a little bit better. And this comes from Paul North. And I think that this diagram is extremely nice because the diagram expresses a little bit what we know and we don't know. And as you can see, there is not even, wrong. There is not even a numbers here, not units, nothing, because of course, I mean, and you know, my colleagues in China are specialists about all this meso scale, and they have done so excellent and good work in that area. And it depends on what is your observation. I mean, you know, meso or micro or macro can be really depending on what is your scale of observation. So I don't have anything there. But for our system, of course, we know in which area we are, and of course, I mean, we are macro will be our particles, and meso will be just what is going on between the equipment and it's more like going from the micro to the bulk. And the dimension is right there, and of course, I mean, we know how the stress behaves when we have the quasi-static regime there. We know when we have the rapid kinetic continuum regime, but what's going on in the middle, it's not clear. And I was convinced up to probably 6 months ago that there was a continuous curve there. And I have to say that just in May, I was at a very interesting workshop in China, organized by Professor Lee, and I think that probably over there is not a continuous link. There might be anything there. It depends which effects take over. There are different effects playing, and depends what it takes over. So it depends also on what the situation, what is our flow conditions, and so on. And of course, I mean, we need to understand these bulk properties. Now, what do we know about the in-between? So meso, it's in-between. What do we know about in-between? Personally, I think that there is still a lot that we need to know, even if I was trying to put down here some, again, going back to my homework, identifying what are the equipment. Some of the processes that we use were actually the intermediate regimes developed. And we have the chemical looping combustion, and for the people who are doing carbon capture, they know that, you know, there is a lot of work going on in that area. There is coal combustion, the biomass gasification, conveying, fluidized beds, and so on. And of course, another thing which I would like to point at this at the time now, because I'm going to touch upon this later, let's also not forget that it's not just hydrodynamics. And I think that you said that yesterday, that we have, at one point we have to start to think about the real situation and just to forget that it's only hydrodynamics. We have chemical reactions, we have heat transfer, so we have to do that. And that's why I was trying to look at this situation. Now, what are the constitutive requirements? If I want to develop constitutive equations, what are the constitutive requirements that I need to take care of? And of course, we start from here, and we have the inertial regime, we have the quasi-static regime, and usually we look for the pressure and the viscosity in the inertial regime, and the pressure and stress ratio in the quasi-static regime. And these are, I like to, and I think that what we are doing, and this is now a philosophical point, and I'll try to, since I have an hour, I'm trying to do a little bit of philosophy as well. Yes, it's a philosophical point for me, and actually I don't have an answer, and I would like really that we discuss a little bit about this later, because this is an important point for me. We do a lot of adding and what I call bolting on. Now, what do I mean by that? Adding, we know what it is. I'll show you some results. We have frictional stresses, we have kinetic stresses, one plus the other one, and that's the total stress. So we add them. And the first thing that bothers me a lot is this on and off. Because if I have the on and off, I'm not able to do the intermediate regime. So that's the first thing that bothers me. The second thing is the bolting on. Now, look at the friction that we add. What do I mean? What do I mean by bolting on? I think the next one will explain better what I mean by bolting on. This is a very used way of modeling granular materials. So there is an area where the fluid, where the flow is dilute, another one where it's more dense. And what we do, we add the kinetic contribution to the stress with the Coulomb expression, right? I have a problem here, because we develop the stress in the kinetic theory in a very rigorous way by following the kinetic theory of gases. And we do averaging integrals and this and that, and we get to the stress, right? Very complicated expression. And then at that point, we are not happy about what we have done. We don't predict what we want to predict. So what do? We bolt on another thing, which is at another scale. So this one has not been developed at the same scale of this. So this bolting on, it might be fine, and if it predicts what I want to predict, of course, the models tell us what we want them to tell us. But the problem is that, systematically and philosophically, this makes me uneasy. So this is the first point that I said, and we are doing a lot of adding and bolting on here, adding the two terms and bolting on another thing. However, we soon realized that, friction is not sufficient. And in fact, agglomerates and people, that dense situations sometimes are called streamers. You call them as you want, it's semantic at the end. But clearly, you cannot predict agglomerates. And if this happens, you start to have problems. And then we do a little bit of more bolting on. And of course, I'm one of the people very much responsible for doing that bolting on. I did a lot of bolting on in my thesis. I continued even when I finished with the work that I'll show you here. This is what we did. One of my first work in cohesion. Now, I call this cohesion. It can be anything which is actually happening between two particles. And what we did is just we tried to have this pressure-like term, which really very much relies on the pseudo temperature, or I'm so old that I still call it pseudo temperature, see? Granular temperature. Right, so this is the granular temperature, and this was the interesting thing. And there was one of the talks yesterday, I think, where there was the gradient of volume fraction. And this is a counter-diffusive term. In other words, we made the hypothesis that when particles get together, there is more chance that other particles are trapped into that. And that's why that term gives the possibility to have this collection of particles sticking together. And what makes them sticking together is that force there, which, of course, I mean, we had to find in the books. We didn't have anything to compare with. But the interesting thing, and these are some graphs which I took from the paper which was published in 2000, a long time ago, was like, these are actually, the continuous curve is a experiment, it's what we predict with our model. And the squares are experimental data that were taken in France at the time, what was still called, and Olivier probably knows about that, IRSID. Doesn't exist anymore, I suppose, but it was, I mean, that data with Molotov and a long time ago, they were taken there, and that is what they observe with small a, with Geldart A particles. And if we were just using blindly the kinetic collisional plus the friction, the Johnson and Jackson approach, we couldn't predict anything. Well, we could predict, of course, but we could not look at the shape, because this is what we predict, completely different. As we started to put in our equation that kind of pressure, which comes from the counter-diffusive effect, we started to have very good prediction with an adjustable parameter, of course, which was that force. Okay, but I have to be very honest with you. I think this was one of my first PhDs. And he came to me after we did that, and he said, these are the results, and said, sorry, I don't like to use the word, but I think you are cheating. It's impossible that you are really predicting that. And said, no, it's true. And then we did and redid. And then with that parameters, we were able to do that. And we did also a little bit of sensitivity analysis. And of course, I mean, as you increase the value of f, you go more and more toward this M shape that we very well observe in this kind of situation. So it is really all about flow and interactions, and of course, oops, why? They are recording me, so they are recording all this. Anyway, so this is it's all about flow interaction. So as you can see, you know, we have many forces that can go on between particles. And another thing which very often, and I'm not going to say anything about this, but Ali has done very nice simulations about this. The bond number has a huge effect there. It depends how big your how heavy your particles are. I mean, if you take a balloon and you put it on the ceiling there and you glue there, it stays. But if you take a ball of steel and put there, it doesn't stay. So I mean, it's clear that the weight has an influence there, and the weight will take as a different slope. It takes over immediately when you go with heavy particles. So what I call cohesion, and again, I mean, somebody now will tell me, oh, probably it's addition, it's not cohesion, but particle, same material should be cohesion. At the wall, probably it's addition. But anyway, let me say that these are these interparticle forces that are there. So we can have chemical bonding, electric charging, and you saw the presentation yesterday, van der Waals and liquid bridges. And that's another thing that I would like us to think a little bit. We are spanning 7 orders of magnitude with our particles. So not so much of a mystery there that, you know, things can change drastically, because, you know, the physics changed with 7 orders of magnitude. So what I'm going to look very much about is liquid bridges, and I was hoping that Christine was here later on, because I think that she has a very nice complementary work to this to present. So I'm going to make sure that I can concentrate on wet particles, and we consider particles with a little bit of moisture. So there are these capillary forces which start to become important, and these liquid bridges start to develop. Again, let me go back to situations where these liquid bridges are, you can find them. So it's coal biomass gasification, and I will show some examples of that, coating, fluidized bed, and so on. So this is our hypothesis. This is what we are doing now in the work that you will see from now on. And in the rapid flow, we consider just that these particles actually don't touch each other. They are just covered with this film of liquid. And of course, I mean, the situation changed because the surface, you are doping the particles, but nevertheless, they are not touching yet. And then you go to another situation, which is this one, when you have the quasi-static flow and you have really these particles with enduring contacts. But you can have this situation here when you have these liquid bridges, and here you have really this dense intermediate flow. Now, what we do, again, we don't tell me that this is again bolting on, this adding, yes it is. Just to prevent any criticism here. So what we are doing here, we are just trying to input another term into our particle-particle interactions, and you see that in the stress, which is written in this way, which comes from the kinetic theory, we are going to in this term here, we are going to have another contribution to the viscosity, which is going to be the wet one, and we are adding with the other stuff. And this is the wet shear viscosity, and we use the two-fluid model, of course, and what we are going to modify are the terms here where you see the stress tensor, as well as the term which takes into consideration the dissipation of granular energy. So these are the two modifications that we do in our modeling. Nothing new, it's not us, but nothing new about these terms. You can find them in a very well published data. So these are really, you have to go back and look very much at the liquid bridges and write down what the force that you have at the single particle level. Of course, I mean, there is the interparticle approach. There is a lot of work which has been done in Sheffield, actually. Adam did a lot of work on this, and you can do a lot also in terms of kinetics. I mean, the liquid bridge can be kinetics, can move, the amount of liquid can also evaporate and so on. There is a lot of work in. We try to make it simple, so the liquid will stay there, doesn't evaporate, and we made also sure that this was the case when we did the experiments using not water, but silicone oil. So we came out with, why do I do this? Because I'm stupid. So normal stress, yeah. Oh, this is a characteristic which runs in the family. My mom used to ask questions to answer the question as well. So I'm the same. I ask the question and answer the I don't know if I want to be registered, but recorded, registered, that's it, recorded. Anyway, so this is the normal stress, and this is the equivalent viscosity. And there is also this lubrication coefficient that we look at the paper by Adam and by co-works, and that's what we have. The other thing that we had to be aware of, that, you know, this was again on and off, and that's again something which we didn't like very much, but it has to be there if we want to do something at this level at least. And there is a critical, you can see what is the critical distance between the particles over which you have to, I mean, in which, sorry, over which you don't have the liquid bridge as such. You have just the particles surrounded by liquid. And this HA here is really has to do with the asperity. So it is a way to compare the liquid bridges with the asperities which are on the particles. And of course, I mean, what one can see in terms of liquid content, because this depends on the liquid, how much, what is the values of H. And of course, this is a parameter that we have to change when we have different amount of liquid in our system. The same situation here, you can do it also in terms, the distance in terms of solid volume fraction, and you can see when is that this term actually start to have an effect. The other thing, of course, I mean, we have to look, if we want to look at the dissipation of energy, we have to look at the restitution, at the coefficient of restitution for wet particles, and again, we have to modify the coefficient of restitution, taking into consideration the fact that there is a stock, depends on the stock number. There is a stock number here, which is again the critical one, which is linked to what we have seen before, and you do this calculation. You complicate a little bit the model. You input it into the model. And that is what some of the results that we have. So this is clearly an additive effect. I put just additive there so that nobody's going to complain that I'm cheating. So it's an additive effect. And you can see that, you know, here, we have also friction. Even friction jumps immediately or on and off at very high concentration. This one is slightly better because it goes a little bit down, but what we would like really to have is more a continuous effect here, which we don't have at this point. Even if we have, I think for sake of time, I'm not going to present you that results, but there is a very good work of Tardos that he did in 1D actually, where there is a different kind of stress which is more continuous. And we made just not long ago, we generalized it to 3D, and we saw that actually you can predict more continuously this kind of interactions. It's not liquid bridges, but it's cohesion that he speaks about. And this is what we get in terms of energy dissipation and granular temperature. So you can do everything you like, and of course, I mean, you can compare with the dry bed and see that, you know, you have some differences there when you have the wet bed. Now these are just a snapshot of some of our experiments. We did experiments on a little bed with electrical capacitance tomography, and like I said before, we put some silicone oil in it. And you can see that very little amount of liquid can really change dramatically the situation. So we go from here, where it's essentially dry, and then as we have more liquid, you start to have this kind of behavior, which of course, I mean, and these are for the operating conditions that you see here. But you can do this, you can repeat it with any other kind of system, but that's what you see in the experimental work. And again, this is what you see in the experimental work. So you can see that, you know, for various amount of liquid, you have different behavior of the bed, which is actually very nicely described also from what we, from the experimental fluidized bed pressure, we drop that we can measure. So the dark one is the dry bed, and you can see that, you know, and these two here are low amount of liquid, and then as we should expect, when you have more liquid, you start really to have these plugs and these channels, and then you increase, and that's why you jump from one situation to the other. So that was fine. We also tried to use our model, and we were very happy up to this here. So for a fluidization, sorry, this is liquid content here, but for this liquid content, which very well agree with what it has also seen, but was seen in 1999 for 1.4 for the fluid digestion index. The model does well, doesn't do anything here because, of course, we are changing regime. You cannot apply that kind of theory anymore. So if we remember when the kinetic theory and all the modifications can be used, it's okay. I mean, we can use it. But I think that we have to be cautious because I have reviewed papers, and also, I'm afraid to say, being external examiner on thesis, where you have very dense regions and people apply the kinetic theory. And that's not acceptable. But people I know get excited, and many people still use it in this way. So I want to switch now a little bit, and I want to show you another system that, again, because of the energy, that we have been looking at in details, and it's biomass pyrolysis. And the reason why I want to do this, because now I would like to challenge myself, not just with the hydrodynamics, but also with the chemical reaction. Okay? So, and even more importantly, there are more than two. If you really want to do the system correctly, there is more than one solid there. So we were lucky to have experimental data from Canada, ICFAR in my friend Franco Berruti in ICFAR in London, Ontario. So this is the pyrolysis reactor, and had a very nice new way of separating within the reactor, inserting this conical separator here, and this is actually a downer. It's not a fluidized bed, and this is what we try to model. So we have a couple of papers published with them about, they provided us with the data, and we did the modeling. How did we do the modeling? Well, we use again the two fluid models, and there are two papers at least, I think, published on this. And I don't want to go into the details. If people want to speak about this later on, I can provide the paper so we can go through that. But the important point here is that we have gas phase, sand phase, and biomass phase. Of course, I mean, we are assuming that the biomass is all one size. But nevertheless, we have two solid phases, so we have to have another equation here for the momentum. And we have to have also the granular temperature, which takes into consideration that there is some dissipation because of the two phases. But more importantly, there are reactions here that we have to consider. What we have to supply that, there are many more closure equations that you need there, of course. So we have to do the gas species conservation. We have to do the energy balance equation on the three phases. And when I say energy, I mean energy. The temperature is changing. So we have to do the heat exchange between the gas and the solid phase, heat transfer, Nusselt numbers. If I don't go into all this, again, it's published, I can show it to you. And then the other thing that we have to do, we have to consider that the biomass is drying and there is a devolatilization. And this is what we take here. And please pay attention to the fact that here I'm only considering these terms. This is what I'm considering. I mean, of course, you can have something else going on there, but that's what I'm putting into my model. And from the literature, we take these stoichiometric coefficients and so on. This is now how the gas-solid separation works, and these are like this is something that we calculate, we model with that equation. So you can see that this is where the gas actually exits. And it's a very good separation, actually. You get almost 100% separation with that conical thing over there. And we are able to see what the sand and the biomass is doing. The other thing that we are able to do, we are going to look at the biomass, the sand, and the gas, and this is, for instance, the temperature, how it evolves along the equipment. I mean, there are many things that you can do. I mean, I just show you some of the results which I thought personally were more interesting. See, it's really very much like it's happening in cracking. You know, everything happens at the inlet, and you can forget about anything else. But of course, I mean, if you have a separator, you cannot forget about that because you have something else to worry about. And in fact, I mean, you can see that, you know, there is also, you can see how the sand is going to be captured, how the biomass is going to be captured. You can see the devolatilization rate of the system and so on. Here you can see how the gas velocity is going to distribute around the conical stuff here, and you can see that for different amount of, I think that this is for sand, for different amount of solid that you put, you can have this different capture of the. But I think the most interesting thing is that if you look at this, you can actually look at what is the temporal evolution of bio-oil, water, and the components that you have put into the system. And this is against the flow rate. So I think that, you know, we have what we expect, let's say. But of course, I mean, we have to really to be able to also to see if this is a qualitative feature, if we are able to predict what you observe in practice with numbers. Now, this is something, we took this work here at ICFAR, they were able just to tell us things about how much solid was collected. We didn't have this data. So we looked at this work here, and we used the data in this work to do the study. And I think that, you know, it's not too bad, actually, if you see what how the prediction compare for the overall product. For the condensable gases, and of course, I mean, here, like I said, you have to be a little bit careful because it depends what we put like reaction. But I think for me, these two things are important here, the CO2 and the CO, it's not bad at all. And the other thing that you can see also the product yield, and again, I mean, you know, this is the you can have the chart, the bio-oil and the non-condensable gases here, and again, it depends. I mean, how you write what you consider in your reactions, and what I really think it's nice. And yesterday we were discussing about, I think it was at lunch, we were discussing a little bit about. The fact that, you know, we want to look at the energy mix, we want to look at the application of these systems, but is this something that we want to do because we want just to be able to predict what we already observe, or is something that we want to do because we want to use for the future in terms of design and do something? So I think that this is why I really like very much. I don't know if I trust the results, but what I like very much is that, you know, we do see some changes, of course, if we start to do a little bit of sensitivity analysis. And I will show you some results at the end in terms if we change, for instance, the temperature, the inlet temperature of the sand, if we change the flow rate. So if we really can believe in that trend, probably we can help a little bit if we want more or less of the products that we are going to look for. And then, of course, I mean, and this is what I mean here when I say that here we have different flow rates of sand, and you can have different temperature profiles and devolatilization efficiency, of course. The same, for instance, if you now change the size of the particles also has an influence there. and you change the yield. And that's, again, something that if you want to look at the trend, and I'm not saying that we have to trust these values, but if you want to look at the trend, I think that in practice you can probably start to see what the model can tell you. Yes, now we did also, probably it's the same like anyway. So what I want to the way I want to summarize now that kind of work is that the product yield depends on the flow rate, and we know that. But the important point, I think, is just that if we really want to have more bio oil, for instance, we know how we could, in which way we could go, and the same if we want to see if we change the particle size, we can know in which way the system is responding. So, in the pyrolysis, of course, I mean, there are applications when you work more bio-oil. There are slow pyrolysis when you work more biochar. So I think that, if you are able with the model to tell you in which direction you should go, that could be a very good thing that the model is able to do for us. Now, another application, there is somebody from BP in the audience, so fluid catalytic cracking. Let's go back to the basic. So, sorry, let's go back to the. So anyway, so this is actually a work, interesting work that I did with my colleagues in Brazil. Was sponsored by Petrobras, and I think that what I like about this work is the fact that I was able really to consider very complicated chemical reactions and have the system working fine. And this is really complicated. It's not complicated only in terms of equations that you have to solve, but it's complicated because you don't know exactly what the kinetics of each single reaction is. And in my previous life, last century, I did a lot of work in lumping kinetics. And lumping kinetics is for people working in petrochemical industry, they know that it's the only way really to tackle very complicated kinetic reactions and a large number of reactions. And you have one lump, 2 lumps, 3 lumps, 4 lumps, and so on. And I remember that my late supervisor, when I still was an undergrad, used to tell me, oh, there are only 3 numbers, 1, 2, and infinity. So if you have more than 2, just don't bother with the summations. They are too complicated. Do an integral. So, I mean, okay, I'm making this, the story is a bit, it's probably excessive what I'm saying, but with this kind of systems, if you really have, so discrete lumping is when you substitute lumps with pseudo components that behave in the way you think that all the mixture behave. But if you have more than 20 reactions, just go with the continuous. So and that is what we did here. And I want to show you how difficult actually this problem is. This is the system we are trying to model. It's just the injector in a riser, and like I said, everything happened here. So that's the interesting situation for the cracking. And this is what we were looking at. So we had the feedstock, which was given to us, and this is any property, but actually we had the boiling point here, but you can have the carbon numbers, for instance, which is related. So this is the kernel. This is the label for the reaction. And then the product, you have the product, which generally what you want to have middle distillate, so you want to shift this and have much more narrow distribution around the area where you like to have it. And now, again, I'm not going to tell you all what we have to do. It's a very cumbersome way of manipulating mathematically, actually. There is a lot of mathematics there. This equation here, but what you can do, you can come out with an expression, and I have to say that I'm extremely happy to present this in Mexico, because one of the bigger contribution in this area. The biggest probably contribution is from the institute, the Mexican Institute for Petroleum. Ancheta, I think, is the person who has done a lot of work in this area, because they extensively use this, because in Mexico you have heavy oil, which you need to crack. So, so anyway, so that's, so this is the way you have an evolution of the weight or of the size of the components just through an integral. And this is what the way the reaction looks like. And this is the bad thing here. So essentially what you are saying is that the balance on a single component, which look is not even with a single boiling point, is the components with the boiling point between, let's say, P and P plus delta P. So it's done by what is already, this is going to be cracked and this is going to be produced. So it's a difficult way to do it, essentially because it's nice to write down, but numerically you know what is going on here, and you want to start here. So you have to go back and back and back and back. And then this is like the distribution that we use, and which again it comes from Mexico actually. And the important thing is that it was very difficult to implement it, because each single step you have to go out, calculate all the reactions with the integral, see if it converts, go back and try it again, and it really takes a huge amount of time. It was done in Campinas, where they have a very nice big cluster where we could do the calculations remotely. Actually, I had the students in Edinburgh, but we couldn't manage it. And now Ali will laugh, because we always make fun about our IT people. So anyway, so and then this is the way it was. We had the 3D problem here. We had this is the way we define all the lamps, so we know what is in each, and these are the conditions. But the interesting thing is that, you see, these are the governing equations that we use, and we use very much the two-fluid model. But again, the very difficult part was now the reaction to be used in that. It's not, I mean, the pyrolysis was easy, very easy compared to this. And we had some results. So dense zone at the everything that you can expect when you have FCC, when you have fluid catalytic cracking. So these are some of the results, and then of course, I mean, what you can see that you have the cracking. However, although we were happy because we were predicting again the middle distillate very nicely, there are huge problems with the coke. So the coke gives really huge problems there, and that is something that, well, we had a project, but then Petrobras was not able to support it anymore, and you know what happened. And but the coke really, it's what gives you the big problem there. And again, these are some of the results, and these are the experiments from Petrobras, and these are the what we estimated. And yeah, there is some problem here, but I think it all goes back to here. But I think that it's really the middle distillate that we were much more interested in, see, like in all this situation. I mean, you know, it's what the product that you are looking for. So I think I'm trying to make some, well, it's not conclusions yet. I have still a little bit of things to show you, which is more work in progress. But these are some considerations so far. The kinetic theory, I don't want to abandon that completely. I don't want to throw it out of the window, but I'm more and more skeptical to use it. Essentially because the intermediate regime, which I like very much to understand, is cannot be predicted, cannot be described well with the kinetic theory. We extended this Tardos model, which I didn't show today, and it's slightly better, but still it's bolt-on. And we are trying something else with the bio-velocity method, which probably has a little bit more flexibility. But I think that the most important thing is that we have to start to worry also about chemical reactions that we have not done so far. And the bolting on, of course, has not been resolved, saying that I have to solve this problem. Now, let me go back a little bit to the kinetic theory, because I want to do a bit of provoking talks now. We know this. I don't need to go through this. There are inconsistencies there, right? So particles cool down, scales, and so on. And you know, I always think, oh, well, geese know that the drag changes if you fly alone or you fly together, right? And we are still not agreeable about what's going on with the drag, right, in particle systems. So this is definitely something. Now, the challenge for me would be really to have a more consistent approach to make sure that, you know, we can have two pictures, one at the microscopic and one macroscopic level, which are simply based on the same foundation. And this is why it's not that I don't believe in the kinetic theory, but I think we have to restart from scratch now and start to do something to develop the new constitutive equations. So my question is really, can we do this? And this is like, and I think that what we need to know the fabric. We need to understand in between that mesoscale what's going on there. And let me quickly, I'm very much advocating that we should do more rheometry, because sometimes we do viscometry without caring too much about the fact that really we can span everywhere here with our systems. And what I mean is that these very nice results from France, from Nancy, show that if you have glass ballottini, it's only glass ballottini, and you are trying to do the viscometric measurements, right? You have a straight line. This is the viscosity, and this is the shear rate. If you oscillate and do the real rheological test, you have this behavior. Glass ballottini. Nothing more than that, okay? So it means that there is something there that we need to investigate for these particles. And I'm advocating that really we need to understand more about G prime and G double prime in the same way like we do for polymers. And we have started to look into the reliable measurements. As you remember, this is another outcome that I have promised and I have to deliver at one point. We bought this FT4, the Freeman rheometer, viscometer probably. But the interesting thing is that it can be used for the quasi-static regime, like a shear cell, and also for fluidization tests, because you can fluidize the cell. Now, we are really very much trying to use this equipment to try to understand what are the constitutive equations, and we realize that we have to understand also the quasi-static regime in order to make sure that we can combine the two. And these are the two, at the moment, what we are looking. I'm much more interested in these liquid bridges, and Ali is very much interested in this tribo-charging. And fingers crossed, let's see if this works. Now, this is just, and we have gone to do some DM, because with the DM we can understand it a bit. Now, you can see here that there is some, this is for the internal friction, this is the attrition, this is sliding and rolling. And you can see that, you know, if you have the rolling, you have more chains here that are starting to develop within the material. So this is something with the DM we are able. And this graph here you can see that, you know, we report the PDF for the system that we are investigating. Now, I think it's just glass ballottini as well. Contribution of the sliding and the rolling. And you see that when you are in this regime, more particles to the weak contact network, When you are in this regime, you have more particles belonging to the strong contact, and you have something in the between. And I think that this is very important. We don't know yet how exactly, but it's important because it gives you the first way to jump from particles to something which is more at the bulk. And this is what we are concentrating on. So, should we abandon the kinetic theory? I have only 2 slides. Yes, I think probably we should try. And this is another kind of work which I don't present here, but it's done with mathematics. And I hope that if in 2 years there is another one of these, I could come again and speak about this very mathematical work here. We are trying to use the dynamical density functional theory, which is very much successful for colloids, and see if we can extend to these particular systems here. It's done with mathematics at University of Edinburgh, which are not exactly our competitors, they are all in our neighbors. Right. So, and we have groups here that actually are good, because essentially what we could do, we could try just from this Langevin equation to start directly to input the collision, the addition, the equation, anything you want. You can put any force there. And I think that probably if we go from particle, and then we scale up, it's much more consistent, and we can go away from the bolted on that I said. So, to conclude, go back to this. What we are doing is we are doing DM at this level. We have been doing, we are not doing at the moment, experiments at that level. We are trying to look at the experiments with that cell now at that level. We are trying to do something we believe between. And of course, I mean, we are to have a smooth merge. And I have learned that, the scale is important. I have spoken only about length scale, but there is also a time scale that I have forgot completely to talk about. The mesoscale is very important. Don't trust models, but I think understand the mesoscale is really important. But I think more importantly, yesterday again this point was made, we need more interaction, more chemistry, more mathematics, more engineering, more of everything, more philosophy probably. And thank you very much. These are the people, some of the people. And actually, he was late. He was not, no, he was away, actually. So, but here is the mathematician. And the interesting thing, Italy, Turkey, Italy, India, Scotland, France, Germany, Algeria. So it's a very multidisciplinary, in the sense of multi-international group. Thank you very much for your attention.